Good day, everyone. I am Engineer Jay Anlomad. I am a research associate from Sarai Project 2.3 Smarter Technologies for Crop Water Management. On behalf of our team, headed by Dr. Roger Luyin Jr., I'm going to present to you our research titled Estimation of Reference Evapotranspiration using a modified atmometer here in Los Baños, Laguna. Let us first have some brief background of the study. The United Nations predicted an increase of global population from 7.7 billion to 9.7 billion by 2050. Coupled with shifting weather patterns due to climate change, the world needs to produce 70% more food to feed the additional 2 billion people. To enable that, we need to have an efficient food production system, not only to feed the world, but also to ensure a sustainable future. Increasing food production requires increase in input that puts more pressure mainly on freshwater resources, which also heightens competition between different sectors. As of now, agricultural water use accounts, on average, 70% of all freshwater withdrawals globally, with even higher share of consumptive water use due to evapotranspiration from crops. Hence, there is a need to strengthen the agricultural water sector with more efficient management strategies, techniques, and measures that will help improve and stabilize crop water productivity. The use of advanced tools and real-time data represents a key strategy for achieving sustainability of both irrigated and rain-fed agriculture. Accurate estimation of crop water use is an important aspect of making sound irrigation scheduling decisions. Evapotranspiration-based and soil moisture-based irrigation schemes are two common bases for irrigation scheduling. Soil moisture-based uses either the standard gravimetric method of soil moisture determination or existing commercial sensors that are installed in the field to approximate the volume of water in the soil. ET-based irrigation uses empirical equations like the FAO-Penman-Monteith to calculate the reference evapotranspiration, using data generated from automatic weather stations or meteorological weather stations. However, daily gathering of agrometeorological data and computation of evapotranspiration is tedious and requires many resources. An alternative for ET measurement is an atmometer. An atmometer is a cylindrical instrument used to estimate the reference evapotranspiration. It simulates water loss from plant and soil through a wet, porous ceramic plate covered with a diffusion cover. Atmometers can be installed and used in areas that do not have a weather station, areas that have microclimate characteristics, or when agrometeorological data are inaccessible. Farmers can use this instrument to generate an irrigation schedule by determining the daily evapotranspiration rate and estimating when to irrigate based on crop water requirement. There are three major types of diffusion covers patented by ET Gauge that can be used on atmometers. Style number 30 and number 54 are canvas covers used when the atmometer is placed in an open area or mounted above the plant canopy. Style number 30 is used to simulate grass and can be used in golf courses, whereas style number 54 is used for agricultural crops and simulates alfalfa. The third type of diffusion cover is called style number C2 and is used in sites where the instrument is installed within the canopy, or the top of the atmometer is of the same height as the plant canopy. This type of cover can be used for any crop. In this study, we used an atmometer with style number 54 diffusion cover. The atmometer was installed at the National Agromet Station here in the University of the Philippines, Los Baños. FAO-ETO calculator was used to compute the reference evapotranspiration. It is based on FAO-Penman-Monteith equation. Data for this calculator, namely maximum and minimum temperature, relative humidity, wind speed, and total bright sunshine, were also acquired from the National Agromet Station. The study area falls under the Type 3 climate of the Modified Coronas classification, which is distinguished to have no pronounced maximum precipitation period, with short dry season, often lasting from December to February or March to May. The data used in this study were measured from October 1, 2019 to February 29, 2020. For the manual readings, reference evapotranspiration was measured and recorded daily every 8 a.m. and 2 p.m., whereas for a digital atmometer, it records every 0.25 mm mark. The daily readings were then processed to generate 3-day, 5-day, 7-day, and 10-day interval readings. The measured reference evapotranspiration are then processed to remove the outliers, by first getting the percent difference of the manual readings with the FAO-Penman-Monteith evapotranspiration values. Then the upper bound and lower bounds were derived using the first quartile, third quartile, and interquartile values. This process is repeated for each interval. Data that are outside the upper and lower bounds were excluded on further processing. Afterwards, 70% of the clean data were randomly chosen and used to conduct a linear regression analysis. The intercept of the line generated was forced to the origin, since when the value of evapotranspiration computed from FAO-Penman-Monteith is 0, the evapotranspiration from the atmometer must also be 0. Meanwhile, 30% of the clean data was used to generate the values to be called as the predicted values, which will be compared to the FAO-Penman-Monteith values for the validation. Percent error and RMSE were used for the statistical analysis. These are the scatter plots in which the linear regressions were generated. Red points for the manual readings and blue points for the digital readings. Atmometer readings are on the x-axis and the Penman-Monteith are on the y-axis. This is the scatter plot for daily, 3-day, 5-day, 7-day, and 10-day interval. The slope and coefficient of determination are shown in the next slide. These are the calibration equations generated for daily, 3-day, 5-day, 7-day, and 10-day intervals. It is considered to be of good estimate if the slope is within 0.9 and 1.1. As we can see, the slopes for each intervals are within the threshold. For the coefficient of determination, it is considered to be of good estimate if it is greater than 0.85. Our minimum coefficient of determination value is 0.92 from the daily reading. For the statistical analysis, we have percent error and RMSE. For the predicted values to be considered as good estimates, the percent error should be less than 5%. For it to be acceptable, it should be less than 10%. As we can see, only 7-day and 10-day intervals were acceptable. That is 0.42 mm and 0.39 mm respectively. For the conclusion, the atmometer is an acceptable alternative for estimating reference evapotranspiration when processed into 7-day and 10-day intervals. Daily, 3-day, and 5-day intervals have high percent error. The atmometer is recommended for crops that do not require frequent irrigation. When used for irrigation scheduling for different crops, crop coefficients are multiplied to get the crop water need. The study's data length was limited by the pandemic. It is recommended to use longer dataset for the calibration. That ends our presentation. Thank you everyone and have a nice day.